Hi, and welcome to part two of kinetics. We're going to now investigate a little bit about what types of mathematical things we can do with this concentration and how we can represent how the actual reactants are affected by different concentrations. So here we're presented with some data, and this data is telling us the instant or the initial rate of increase of a product, and then they give us initial concentrations of the reactants. And so we have the balanced equation up top where we have the ClO2, the F2, and we end up with ClO2F. And so the product is what we're measuring the increase of initially. And the reactants are what we're coming up with the initial decrease of. And so if we looked at our, say, graph here, we're looking at the instantaneous point in this graph, the very first point right here, right when the reaction happens. The rate of increase of product and the rate of decrease of reactants. So we get figures for that, and this chart provides that information. Well, how we represent this particular information is in something that we call a rate law. Now, in part A of this question, it says write the rate law for the reaction above. Well, generically, a rate law is going to look for this reaction something like this. The rate is going to equal a constant, which we denote as K, times the concentration of the reactants times the concentration of the other reactant, which is F2. Now, each of these reactants has what we call a particular order. And I'm going to show this order with an X and with a Y. Now, X and Y are just two unknowns. And now, what this is telling us is, does a change in concentration of either of these reactants affect the overall rate? Now, the only way we can find that out is if we change the concentration of one of them, and in doing so, then figure out if that affects the rate. And we're presented with data that will allow us to do that, is really what it is. And so we can't look at both simultaneously very easily. We have to look at each separately. And we have to compare different experiments that are shown up here. You'll notice that up top, there are, well, three different experiments, 1, 2, and 3. And so for each of these experiments, we have some data shown. And what I'm going to do is I am going to take one experiment in the form of the rate law and divide it into another and see if I can figure out what the x and the y are. In order to accomplish this, I need to pick two experiments in which one of the reactants is held constant and the other one changes, at least initially. And so for the first comparison, if we look at the experiments, the rates change. Two are the same, but look at the initial concentrations of the reactants. And you'll notice that between 1 and 2, the ClO2 remains at 0.01 and 0.01, whereas the initial concentration of F2 goes from 0.1 to 0.4. So I am going to divide experiment, well, 2 by experiment 1, the larger by the smaller. So I'm going to divide 2 by 1. And in doing that, I'm going to put the rate law in an entire horizontal row above the other rate law. You'll see what I mean. So I'm going to take 9.6 times 10 to the negative 3. And that's molarity per second. I'm leaving the units off for the sake of saving space. Divided by 2.4 times 10 to the negative 3 equals the K times concentration of ClO, 1 to the X, and 0.4 to the Y. Now notice how that total horizontal top, 9.6 times 10 to the third equaling K, 0.01 and zero point 0.4, that's going all the way across experiment 2. Whereas experiment 1 also has the K, which is unknown at this point, but you're going to find it's a constant, so it stays the same for each experiment. And here we have 0.01 to the X and 0.10 to the Y. Now, the beauty of this is that the k's remain constant the whole time, so the same value over itself cancels. And 0.01 to the x and 0.01 to the x will also cancel. And so then we can divide 2.4 into 9.6, and that comes out to, well, 4. And then that equals zero point 0.1 divided into zero point 0.4, which is 4 to the y. Now, you may very well see that 4 equals 4 to the y is 1. Well, the way we could reconcile this with logs as well is we could say the log of 4 should equal y log 4, and then we could solve for y, and we're going to find log 4 over log 4 is 1 anyway. However, sometimes you won't get a number that's quite so nice. So what we're finding here, which I can erase our y and say, look, y is 1. We call that first order. Well, I did all that mathematics in order to figure out that y was first order. Now I can do something similar, and I'm going to for the x. However, I can't compare experiments 1 and 2. I need to compare experiments either 2 and 3 or 1 and 3. And I'm going to choose 1 and 3. I'm going to erase what I have here so I have some space. And now let's compare experiments 1 and 3. And I'm going to divide 3 by 1. Now this isn't quite exactly as nice and clean as the other because both the F2 and the CL2 change simultaneously, right? And so we're going to take 3 and divide it by 1. So I'm going to put the rate, which is 9.6 times 10 to the negative 3, divided by the 2.4 times 10 to the negative 3. And then we have our k's, which are going to end up canceling. But both terms are going to be important in this case, because here we're going to have 0.02 to the x and 0.01 to the x. And for the other term, we're going to say, well, 0.2 to the first over 0.1 to the first. Now I could put the first in there because I solved for y, and y was 1. And so now I can actually reconcile this a bit in the fact that 9.6 divided by 2.4 times 10 to the negative 30 comes about 4 equals, the k's cancel. Nothing else will though. However, we can take care of our numbers and the exponent will persist. So 0.02 divided by 0.01 is 2 to the x times, well, how many times is 0.1 going to 0.2? 2. So then let's divide by this side by 2 and divide this side by 2, and we end up with 2 equals 2 to the x. And hey, x ends up being 1 as well. And that's excellent. And so our x is also 1. And so we found out, well, what the orders of each reactant were and put it in the format of a rate law expression. The overall order, we add up the orders. And it's the second order, and the reason because 1 plus 1 is 2. Now we can solve for the K, and the reason we can do that is because now that we know the order of each reactant, we can put it into a particular experiment, and we'll know everything but K at that point. For instance, let's just take experiment 1. Experiment 1 is 2.4 times 10 to the negative 3. And that's going to be what? Molarity per second? Equaling the K, which we don't know, times 0.01 to the first and 0.1 to the first. So now we know everything but the K. Remember, these brackets stand for molarity. Mathematically, we're going to get 2.4. However, let's pay attention to the units, because in reality, we're dividing molarity per second by molarity squared. And what I'm going to do is I'm going to draw just a, well, mathematical expression as far as how this goes. I'm just erasing the bottom of this so I have some space. So now let's take a look at what I did. The rate over the two different sets of brackets equals the K. Well, that means that we have molarity per second over molarity times molarity. Well, you bring molarity to the numerator, and you get 1 over molarity, and that cancels that molarity out. And then we have this other one left over. And so we're going to have 1 over molarity and 1 over seconds, which we show as molarity to the negative 1, seconds to the negative 1. And there is our rate constant, and we've specified the units. Now remember, the units are important. They're half the credit. They're not always going to be identical. It depends on the rate law expression that we're working with. Fun times. Let's go to part 3. Hope you enjoyed part 2.